Hey, Phi Sci people, welcome back to class. I know that notes aren't your favorite thing, but I've going forward with all these. I'm hoping we have shorter sessions of notes. Now today's is a little long, but after that I break them into smaller chunks. And because we're not doing labs anymore, I don't think we can do labs, can we? I have some little interactive simulations for you to try after each of these note sessions as we go. That'll replace the lab work. So you don't have to write these notes down. I'd appreciate it if you hung around and listened to these. If they're that terrible, hit it's a YouTube video, so you can go down and change the speed, and you can double up the speed on my delivery. And I might sound like Mickey Mouse, but you can get through them quicker that way if you like. Anyway, we're going into pressure, fluid pressure specifically. And what is pressure? Well, it's a push that the fluids exert on an object. So, you have a glass of water. Well, there's water in that glass is pushing down and to the left and right. The air that is in your room or wherever you're watching this video from, the air is pushing down and left and right and even up from the bottom. And as far as fluid goes, fluid include all kinds of gases, air, and liquids as well, because they all kind of act the same with pressure. As long as there's gravity around, there's pressure from fluids. All right. So your heart is a good demo for your own self where there's pressure involved. The heart pumps the blood through your body. That's a little graphic, isn't it? All right. Fluids are liquids and gases alike. So again, you boil some water, you get gas coming off. That's a fluid, and the liquid inside the kettle is a fluid. Any kind of water shooting out of a hose, or in this case, Old Faithful, is also a fluid. All fluids exert a pressure. Again, if there's gravity around, and everywhere I go there's gravity, I hope the same for you, there's pressure. If you take some fluids, gases, or liquids out into space where there's no gravity, then it's just floating there. There's no pressure. It's caused by the mass of the fluid and the motion of its particles. It's a force that acts over a certain area. So again, there's air above our heads, all the way up to the thermosphere, if you remember your Earth and space science. And all the air above us has weight, mass, being pulled down by gravity. It's pushed on your head. It's pushed on your side, your armpits, backside, under your feet. It's pushed in all directions. And here's a way to visualize that air that's around you and above you. Each little blue dot on the left here is a particle of air in the atmosphere. And as you go higher and higher in the atmosphere, you can see there's less of them. That's what happens to our atmosphere. But that's still combined weight. So all that weight above your head, like on the right side picture, the little dots, they thin out as you go higher, but that's still mass above your head, pushing down on you. Anyway, the units we measure with for pressure is newtons per centimeter square. Again, newtons of force. Centimeter square is an area. So pressure works on an area of your body. Normal pressure is 10.13 newtons per centimeter square. Yeah, that's metric. Real world numbers, about 15 pounds per square inch. 15 pounds per square inch. That's a lot of pressure on just 1 square inch of your body. Now, the air pressure outside and inside the body are balanced forces. Now you remember balanced forces. Those are where the forces are equal on both sides. So the book on top of the table, or maybe your Chromebook sitting on top of the table. Gravity's pulling it down, tail's pushing up, it ain't moving, balanced. Well, these slices of the body here to show the inside and outside are balanced forces. Pressure on the inside is pushing out, so you don't feel that mass. Believe it or not, there's about 19 tons. Yeah, you heard it. Go back and replay it. 19 tons of pressure on your body from all the air around us. But we don't feel it because it's equalized by the pressure inside. Differences in pressure, what that may cause, that's what we're going to get into here. Pressure varies directly with depth. So if you go up in an airplane, you've probably done that, or if you drive your car up a hill. There's a couple of hills in Berks County, up past Hamburg, Pinnacle area, or up Pricetown. As you go up the hill, you feel your ears pop because there's less pressure in your ears, and you feel a little sound, the pressure release in your ears. As you come back down that hill later on, when you're done, you can feel the little bit of pressure inside. It may hurt a little bit. Increase the pressure as you go down deeper into the fluid or the air. fluid pressure is exerted in all directions. Again, it's pushing down, left, right, up, all equally. Doesn't matter where you go within a fluid, it's equal pressure all around. Fluids can move from areas of higher pressure to low pressure. So hey, you spray that can, whoosh, it comes out of there because the high pressure inside the can goes to the low pressure on the outside. Weather systems from your Earth and Space Science days, high pressure systems where the nicer weather is, it rushes towards the low pressure and the air rises through those. So it all works together in all different formats. Even your breathing. When you breathe in, the diaphragm contracts. That's in the left side picture there. That contracts. And in other words, it allows your lungs to get larger volume. And there's a bit of a vacuum in there. And the air outside, outside the room that you're in, gets sucked in through your nose or your mouth, fills your lungs. And then when you exhale, which is on the right, that diaphragm is pushing up. It's making the volume smaller in your lungs, and the air is coming out of you. That's how you breathe through your diaphragm. So the lungs aren't really sucking. It's a muscle pushing it in and out. And the pressure on the outside forces that air in. You vacuum your car. Yeah, I have done it in a while. In fact, when I do it, look at these nice lines this guy does with his. I just get the dirt. It's clean, I'm done. But same thing, the motor pulls the air in through the hose, dirt goes up, gets trapped inside there. Suction is another way. You have a suction cup or Spider-Man. You have a little vacuum inside that suction cup. Probably have them hanging on your refrigerator or maybe on some windows around your house. Inside that little cup is a vacuum. The pressure on the outside is pushing in on the rubber part, holding it to the glass. It's unequal pressure. Low pressure inside, high pressure on the outside. The air is trying to get in, but it's blocked by the seal. When you're drinking out of a straw, you create a vacuum by sucking the air out of your mouth, and the pressure outside is pushing down on that drink. So you're having your little latte here, and the pressure is pushing down that cup. Latte goes up the straw. You're caffeinated. You're ready to go. All right, hydraulics. I don't know anybody who has one of these kind of cars. Here's another one. But you've all seen front loaders or the equipment that digs dirt. I just forget the name right now. But those all use hydraulics to create a lot of force using liquid pressure or fluid pressure. All right, hydraulic devices use the principle that pressure is transmitted equally in all directions throughout a liquid. So when you're looking at a front loader or a backhoe, that's what I wanted to say earlier, backhoe, they're digging the dirt up. They have a fixed pressure in those lines, and they can create a lot of strength from that pressure being moved around through pistons. And I'll show you a little bit about that in a moment. So a force acts on a small area and produces enormous pressure in the liquid because it cannot be compressed. So this picture I have, let me explain this a little bit to you. This here's a brake pedal. So here's your foot, okay? And you're pressing down on the brake pedal. There's your brake pedal. God, that's an awful foot. This is the toe, this is the heel. You're pressing the brake pedal, pushing down. You push down on this little piston on this left side. The pressure increases inside all this brown liquid in here. But it's equal throughout. And as it's pushing on this larger area, there's a much larger area here than over this way, that creates greater pressure because this pressure is equal per square inch. So each square inch has a lot of force pushing that car up. I hope that made sense. So force is transmitted throughout the liquid to a larger surface. So this guy's pressure, he only weighs 200 pounds maybe, but this area, the area below that piston on the left, here we go. That's a small area. You can't see it, but the pressure is the same throughout. And when it reaches this larger piston over here, it has much more force, and you can lift things much heavier with the same amount of force. A piston with the largest area will have the greatest force. So here's a good example. I'll give you some numbers here. You have a small weight here on the right. Over this time, you push down with a small weight, and you're able to increase strength by pushing this weight up that direction. Now, what you lose is distance. So you may push down here like 10 inches going down on the right side. You only get 1 inch over here, but you can still lift things 10 times heavier. So this is a mechanical advantage you get with pistons. I wish we were at school, man. We have a cool lab for this, but we ain't going to be able to do it. All right, car jacks, the same, another example, barber chairs. Gosh, you can't even go there to get a God, man, I cut my own hair, but some of you guys probably have hair getting a little crazy because the barber's closed, right? Ladies, no dude, no fingernails. All right, car lift and car brakes. Again, when you press on that on your brake pedal out here, this is your brake pedal, you're pushing down this way, it's a small little piston. That pressure goes to each of these calipers here, and it's pushing with a great force, pushing those together, giving you a lot of stopping power. All right, we'll do that one next. Now, there's a couple little assignments for you to go to. For your assignment, please go to the two links. One's called gas in a syringe, and the other one's called leaking tank. And let me show you those quick. For the gas in a syringe, you'll go to this thing called Edge Media, and you have a few moments before they ask you to log in. And as you see, I have the login information included with the link. But when you get there, you can show the molecules by hitting that button. You'll get to see them dance around. And then close the syringe and see what happens with the gauge. Observe what happens to the spacing of the molecules as you compress the syringe. Then go to two syringes, and as you're squeezing the one in, watch what happens to the other one. Now, when you get the subscription, this is when you have to enter your login information, which I have included there. It's COVID-19 and Edumedia. It's free stuff for us. Then, for the other link, which is the leaking tank, again, it's called this different site, CK12. Another free one. You might have to log in here also. Just use your Google login information, and you'll be right in. So it has this tank with full water. And as you know now from the notes, the deeper you go into this fluid, the higher the pressure. So as you drag this red button down, this red hole, this is the leak. See, the water is shooting out because there's higher pressure down below. So if you had like 3 or 4 holes in this tank, they'd all shoot out at whatever, based upon what pressure is there. But you can drag it up and down and see the distance then changing at the bottom of the screen, how far it shoots out. And then there's a little story over here on the left, if you could just read through that briefly. And then hit the challenge me button. There's a couple questions there. Some of them I know you're not going to know the answers to. Some of them are very easy. It just matter looking at how far out the water shoots. And that'll be your assignment for this first class. So work on those two things, and that'll be it. All right, folks, we'll see you in the next one on Friday.